That's just for the sake of the... Can you read it?
The swap of the Tuesday group theory lecture to 2 p.m. in E0.32 has now been moved or mode on the timetable.
Made.
Please let students know this afternoon at 4 p.m. lecture, whoever is taking it. I've also posted a Moodle announcement to students.
It did look like Putin.
It did look like Putin, didn't it?
Like, was that one of the blowy sucky things that forensics use at school? Inside.
Yeah.
Blowy sucky things in.
They're called Putas.
Are they?
Yeah.
Ah. What with the little ball inside?
Maybe.
There we go.
Okay. So much for that. So tomorrow we're doing 2 p.m., not 1 p.m.
That's fine.
It's fine with me because at 1 p.m. I'm doing decision maps.
Bit of a jump.
Not slow. Did you get the announcement by Norman?
About tomorrow.
2 p.m. lectures tomorrow, not 1 p.m.
The only switch has gone through.
Okay. So we're doing chapter 14 called Group Actions. Is anybody watching? No, nobody's watching. So they can't tell me whether they can see it clearly. So which do you prefer? Do you prefer less light for your scribbles and more light? Or more
This is fine. I think.
All right, and then you can see perhaps better, a bit better on the screen.
I like experience it. I can do it.
Okay. So what is a group action? Sorry, I didn't mean to do it while you were drinking. Quite early on, many weeks ago, I think I told you should, as well, always think of a group as transformations of something. Okay, so not only you have the group elements and they multiply somehow, but it's always good to keep in mind that the group elements perhaps are some actions on something. Okay, so for example, permutations of a set. Okay, so or there was another one which was clearly the dihedral group. Somehow you think of the elements as transformations or some sort of thing working on the n-gon. Okay, and things like that. Yeah? And this is what group actions mean. Kind of, so capture this idea of the group having some outside effects on something. And you can compose the things on the group, not on the group, on the set. So when you rotate it and then you rotate it again, that's like having a rotation, which is the product of the two rotations acting it on at once. So this is what a group action is. It captures this phenomenon where the elements of the group are some transformations or something on a separate set. So the formal definition is like this. You need a group and a set. So let G be a group. And X set. And then call it left action here. Okay, I'll say while left. But what it is a mapping which goes from G cross X to X. Cartesian product. And so this consists of pairs, G cross X. The Cartesian product is one element of G and one element of X. So whenever you take an element of G and an element of X, so you assign it something, and that something is usually written as GX. Okay? It's just a kind of a notation thing. But, so it's not group multiplication necessarily. It could be, but typically it's not group multiplication because typically the set X, or typically, a lot of the time, set X is not the group. It's something completely different to the group. So that's that. But it has to satisfy some conditions. And the first condition is, well, EX. What do you think EX should be? So E is the identity.
X.
Yeah. For all X's. And the second condition is that if you take the product in the group, or a product in the group, what you get is the same as if you first do the one transformation on X and then the other. Okay, and that this has to be true for all possible values of these things, and that's the definition. Okay, so it's very simple. Try to digest it. Okay, where's the left action? Or we could distinguish it from a right action, which I would write the opposite way, so G, and then the composition would work the other way around. Okay? But we won't do any right actions, so all our actions, I believe, are going to be left actions, as far as I have had a look in the book. But there's no need, really. You know, it's like it's not really, not even. We don't even distinguish it in any way. It's just the way the group operation behaves with respect to composing these things. Okay, like this. So note one is that for any group element and X, and X and Y in X is what you get is, okay, so the missing third bit, which is the inverse. Okay, so we said that the group usually when it has some sort of a group-like property is that the identity acts as the identity or doing nothing. Kind of. Elements, that looks very much like associativity. But it's not associativity because X is not from the group. And then the third thing is always inverses act like inverses. Okay, so inverses act like inverses means that if you act on X and get the Y, okay, then what you want is if you act by the inverse on the Y, you want to get X back. So proof of this is an exercise. It's an extra exercise, not in the book. So that's that. Now, some examples, I've mentioned those examples, so I'll just also in the book. So G is the general linear group of 2 by 2 invertible real matrices, and the space it acts on is the plane. Okay, and I've not said much, have I? I'm probably supposed to say more. Yes. So normally you should say, oh yeah, that's linear algebra. but maybe there's not enough linear algebra in what Steve is. But well, I shouldn't be saying these things. I know.
It's all slanted.
But this is fundamental to linear algebra. So okay. So in some sense, so what are these? These are 2 by 2 invertible matrices. Okay, but you remember matrix multiplication. Yeah? So if you have a matrix, now I want to get one that's invertible. So maybe this one is invertible. Okay, and you can multiply a point with coordinates x and y, say. What you get is point. And it'll be x plus 6y, the first coordinate, and the second coordinate is 3x plus 2y. Yeah. So you've got a mapping which, to any point xy, assigns this point. I'm not going to the right again. And such mappings are called linear mappings. Right, or linear transformations. Have you done any linear transformations in linear algebra? Does that ring a bell? Yeah? Did you say that they all correspond to matrices? Maybe not.
I think the way to it was the matrices. We just assumed that.
We do, yeah. Everything is just assumed to be a matrix.
Mm-hmm.
Right. Yeah. I think I remember.
So yeah, so anyway, this is an example. So, yeah. So matrices, linear mappings, and the Euclidean space. It doesn't have to be 2, it can be any dimension. Yeah. That's an inlet. So not only, so you see, not only the group somehow works in itself, but it also kind of transforms points in the plane. Right. So it moves points around and it acts on that space. But how about these 2 properties? Or these 3 properties? Well, you know that the identity matrix, that's the 1, 1, 0, 0. When you multiply xy, you get xy. So it doesn't do anything. And this, you probably also know, it's kind of associativity of matrix multiplication, because you can think of the vectors of 2 by 1 matrix as well. So the advantage of having many different viewpoints of the same thing. So this also works, and you know that if you take the inverse matrix, so this kind of shifts the whole thing. So it's like linear. It can translate, and well, it doesn't translate because you have to. Well, 0 has to stay put in a linear transformation. If you put 0, 0, you always get 0, 0. But the other things, it sort of rotates and expands. Or if you take the inverse matrix, then just them back. It's quite nice, but anyway, this is an example. Another example. So if I take the group, which is the dihedral group, what could it act on? What could the set X be? Did you remember the dihedral group? The definition or description?
Well, a 2D shape with four corners essentially. So if it was D3, it would be a triangle. D4 would obviously be a square.
Yeah.
And appropriately, we number each corner.
Okay. So we could say 1, 2, 3, 4, and think of them as vertices of a square.
Yeah.
Okay, and then when you take the rotation, it just moves 1 to 2, 2 to 3, 3 to 4, 4 to 1, and the reflection moves however you.
Yeah, 2, 1, 4, 3.
Whatever you remember this. 1, 2, 3. So we could have this reflection. Was it called S? S?
Reflection we call S, yeah.
So S1 could be 2. S2 could be 1. In that notation that we have there, G times X. So these are the X's and these are the G's. Is that anything wrong there? Might be a mistake. I'm sorry, carry on.
Half asleep.
Half asleep, but still at least half of it you should get. So this one is there, this one you don't. Okay, but also we could have an action. Can have D4 acting on another set S. For example, -1, 1 squared. So this is the square. So this is really the interval -1, 1. Yeah, so all pairs of real numbers, all points in the plane with coordinates between -1 and 1, both coordinates. So we get a square like that. And then not only you have G acting on the vertices of the square, but any point in the square. So if I take this point here, it's my X, let's say it's, I don't know, 1/2, 1/3. That's a point in the square with these coordinates. Now if so the symmetry, so Sx, then I would get -1/2, 1/3. Okay? And the rotation, I don't know, you'd have to work it out yourself. So the rotation would mean I do a 90 degrees here. And there I would get a new point, and I don't know what it's called, or you could work it out from, I don't know, sines and cosines or maybe something. Okay? So the same group can act on many different things. And these are related, but they can even be. How fast are we going? Not very fast. Okay, so there's another note. Is that for any set whatsoever, can you find a group that acts on X? It's in the book, so it's fun. You can take all the permutations of that set X. So all bijections, it's permutation group. No matter whether the set X is finite or infinite, you can always find the group of all permutations of that set. And yeah. And then actually not only Sx acts on it, but any subgroup you take. In the obvious way, because if you take pi, that's a permutation in X, and of course a permutation that is a mapping, so it maps X somewhere. It's quite easy to I think this is very abstract. Oh. That's true, but it also acts, for example, on all the pairs. I think it's in the book. Well, this probably isn't because you didn't know. So if you take a pair xy, elements of X, then obviously what pi is going to do to it is, well, you do it separately on the
Operator.
That's like the definition of the action. Where you can create those things. Sorry?
Something like that.
Okay. I don't know. I feel like I should be drawing more pictures. I'm probably exhausted. Okay, let's yeah. So there are two important examples. So important example 14.3. And this is where G is a group. And the set it acts on is the group. Oh, I wanted to say something here. So before this. Sorry. So in fact, so in any action, when you fix one element, and you look at the mapping which takes any element from the set X and gives you Gx. And this is a permutation. Okay, so it can't, when a group is acting on a set, can't have an, so every element defines some mapping on the set X. Okay, so you've got the set X. I'll draw the picture. And you look at an element of X, and G and G is fixed. And this moves somewhere. And this is Gx. And this moves somewhere, and this is G squared. G squared. And this moves somewhere, and this is G cubed X. And maybe this moves back, and so on. So that could be, many different things can be happening. But when you take one particular G in the group, one particular element of the group, what it does to the set is a permutation of the set. So it can't identify two things, can't map two different things to the same one. And it has to be onto, so everything has a predecessor. So bijection of X with itself.
Surjectivity. Yeah.
Okay, that's observation. So this is exercise. I hope it's true. It must be. You should be able to prove it from the definition of action. In fact, it has to be true because because what G inverse does has to be the inverse permutation. So it wouldn't work if it wasn't. Okay. There. So this is a group acting on itself, and so G acts on itself. By left multiplication. Okay, so you remember we had this lambda G, which went from G to G. It was which was multiplying by the element G. So then the action takes G and X and sends it to lambda G of X, which is Gx. And now the Gx really is the product in the group because both G and X are from the group because X is equal to G. So this is something that will be useful later for the Ceilidh theorems as well as other things. Okay. Important example 14.4. It doesn't look like an example because it's very abstract still. So that means that you've reached a certain level of mathematics. Where examples look like theories. Examples that have numbers in them are boring. Okay. What are we doing? I'm just watching the video. Now, G doesn't act on itself, but it, so G is a group. And X, I'll call it H, is a subgroup. Oh no, what am I doing? Go away. It's actually the other way around. So this is X. Looks like a smiley. But it's X equals in bracket. Okay, so yeah, so actually H acts on G by what's called conjugation. Has Gillian done any conjugation with you yet? Have you not?
Conjugate. Isn't it assignment? Also.
Possibly.
Yeah, I swear one of my previous other conjugate.
I know who's
So H moves the element G, not this time not to HG, but to G inverse.
Yeah. That was normal for Marty. That was it. Maybe it's two.
Okay, so for each of these examples, you can verify that they're actually actions. So that's not very hard to do because when you take the identity here, you get E times X. It's going to be X. Or group multiplication axioms and the same thing for G1, G2. X is going to be G1, G2X. So that's now associativity in the group, really, for this action. And again, if H is the identity, then G is G. And if you take H1, H2, and let's act on G, you get H1, H2, G. So inverse, H1, inverse, which you can do the inner conjugation first and the outer conjugation, or you can multiply the two elements, no matter which way you do it. Because of group operation associativity, you're going to get the same result.
No.
What else? What else do we want to do? There's like plenty of stupid examples that you think are useless, but they will become useful as we progress. So, okay, I'll skip example 14.5 because I don't feel like doing it now. You can read it, but I can move on to the important thing, which is G equivalents and orbits. Okay, so let G, we have an action of G on X, and we say that X and Y, G equivalent. Group theorists are very sloppy with the terminology because they say G equivalent, but in fact it's not just the G; it's also the action that is part of it. So they just kind of ignore the action. The G can have different actions on X in theory. So saying just G equivalent is a bit sloppy, but this is what people do. And they're G equivalent if, we're moving back to this picture, they're G equivalent if there is a way to take an element of the group that moves X to Y. Okay? So if there exists something in the group that moves X to Y. It's not true for, not proven. If you take any two elements of the X, but there's always something in the group in any action. Always true. But if it is true, if there exists some element of the group which moves X to Y, then we can say that they're equivalent. Okay. Good enough, I think. So we write like this, or even like this, because sometimes the action is clear from the context. So
It's conjugate to Y.
no, it's not conjugate. In this case, it's just G equivalent. Conjugacy is a special example because conjugation is a special action. So being conjugate is an example of G equivalence for this particular action. Okay?
Yeah.
Well, H equivalent. Why are we doing this? Okay. So why is it called G equivalent? I think one should suspect that it actually is an equivalence relation.
Then it holds the same amount of elements, value.
What holds the same amount of elements?
G. So within the group G, there is a finite amount of elements, value, whereas X and Y have the same amount. So say we have 20 elements in G, there is X and Y have got the same amount.
Of
Like in value.
things equivalent to.
Yeah, as in like,
Oh, yeah.
like value. Obviously, here,
It's not necessarily.
not true.
Oh. No. But there is something else that's true. Okay, so the proposition is that it's actually an equivalent relation. So let G act on X, then the G equivalent is an equivalence relation. On which set? because it ties the x and y. So how does one prove that something is an equivalence relation? It has to be these three things. What are they?
Look.
Reflexive, symmetric, and transitive. The first time you see it. Okay, so reflexive means that every element is equivalent to itself. And this is true because. So what does this mean? This means that there exists something in the group that shifts x to x. What is it? Yeah, what is it? The identity? You say? I didn't hear. Yeah, so the identity takes x and puts it to x, and therefore x is puttable to x. Symmetric is that if x is puttable to y, then y is puttable to x. Because? Because the inverse, yeah, exactly. So because if that's an exercise. That if G is the thing that puts x to y, then G inverse is the thing that puts y to x. And transitive, so transitive means that if x is puttable to y and y is puttable to z, then x is puttable to z. And that is true because
you can make a product of what made x go to y and then y to z, and just make a product that still has this within the first group.
so if G1 is the thing that puts x to y, and G2 is the thing that puts y to z, then G1, G2 is the thing that puts x to z. That's the second axiom, or second point in the definition. That's the first point in the definition. That's the second point of the definition. That's the remark that we made immediately after the definition, I think, somewhere around there, which you can prove from these properties and from the group properties as an exercise. And we still have 5 minutes. So the equivalence classes this is a definition. So again, the definitions are boring. I mean, everything here is boring because it all starts with G acts on X. When you have an element X, its orbit is, it's called OX in the book. Its equivalence class, it's G equivalence class. Okay. So what's it like? You've got some group and you've got acting in the set X. Okay. And you've got some element. And then you look at all the elements of the group. Okay. So some of them send it to itself, and some of it send it somewhere else, and some of it send it somewhere else. And everywhere where you can get within the set X, that will be one class. And then you'll have another one for some other elements. That could be more of them. And each of them is puttable by someone in the group to every other one of those. And like this, you split your partition the set X into orbits. Now, we're running out of time, but what we're heading towards tomorrow is the size of the class depends on how many elements are there. So normally, so typically you might expect that. That was, I think, what you said. You were suggesting that all these things should be the same size.
Yeah, somewhat.
So if the identity is the only element that puts X onto itself, and every other element puts it to something else, okay? And then you would have the size of this orbit would be the same as the size of the group, because you have identity sends it to X, and every other element sends it to something different. Okay? If the identity was the only element that fixes X. It can happen that you have several elements that fix X. Turns out they have to form a subgroup. But then if you, for example, if you have a 2-element subgroup that sends X to X, then you only get half the size. And so you can get different sizes for different orbits. So the way a group behaves in this orbit can be different to what behaves. And that's what we're heading to. Any questions?
About something unrelated.
We need to digest it overnight and then come fresh tomorrow at 2 o'clock. Don't forget.
Yeah.